All right, so for those of you who don't know Elliot, Elliot started out as an intern with the Chapel team. We hired him as soon as we were able to, once he finished his school. And Elliot has kind of worked himself into a position where I referred to him a couple of years ago as our pit bull of performance. And what I mean by that is you sort of point him at a performance problem and he just dives into it and won't let go until that performance is wrestled to the ground. About, I don't know what it was, 6-9 months ago, as Arkouda was coming onto our radar and becoming more and more interesting to us and to users, we sort of suggested that maybe Elliot should spend some of his performance time looking at Arkouda. And through that, he's made great progress in terms of improving the performance and scalability of it. So that's going to be the topic of his talk today, kind of following up on what we just heard from Bill about work that Elliot has led and in terms of getting better and better performance out of Arkouda. So Elliot, take it away.
All right, thanks, Brad. Yeah, the pit bull thing always cracks me up because I think that's accurate both for the good and bad connotations of it. Like, yes, I sink my teeth into something, but then have a hard time letting things go when it's time to move on. But anyways, so hi everyone, my name's Elliot Ronaghan. As Brad already mentioned, I'm a member of the Chapel team, and typically I work on performance optimizations to Chapel itself. And more recently, I've been collaborating with users to improve the performance of their applications. This talk is going to focus on adding message aggregation to improve the performance of sorting on Arkouda, particularly on non-Cray networks. And as Bill has already mentioned, sorting is a really critical operation in Arkouda, and it tends to be the rate limiting step in most workflows. So it's one that's really important to optimize. And as a preview or kind of a teaser for this talk, we've achieved more than 1,000x speedup for sorting on InfiniBand networks. And this is a performance scalability graph that we're going to see a lot during this talk. So I wanted to take a moment just to kind of walk through it. So it's a performance graph, so that means that higher is better, and this is in gigabytes per second. It's a scalability graph, which means that the x-axis is the number of nodes or locales, and for this graph, we're showing up to 32 nodes. We'll have another set of slides that show up to 512. And then this is for Arkouda's argsort. For this, we're using 3/4 of a gigabyte per locale. We have some that will use 16. So that's kind of the general format of these graphs. For this particular one, this solid blue line here is the Cray CS InfiniBand numbers currently, May of 2020. And this dashed blue line is probably pretty hard to see because it's hugging the x-axis, but this is where we were when we started this effort 6 months ago. And so this talk is going to focus on why was performance so bad before, and what have we done to get up to these new levels. And something that I think is important for most performance talks is just giving you kind of an overview of the configuration that we've been running things on. So most of the results that you're going to see today are going to be shown for a Cray CS and XC system. So a Cray CS is the cluster line with InfiniBand networks. We're going to look at results on a 32 node system with 56 gigabit per second InfiniBand that has over 1,100 cores. And that's the system that you just saw in the last slide. And we're also going to look at performance results on a 512 node Cray XC, where XC is the high-end supercomputing line with the Aries interconnect, and that has over 18,000 cores. And these systems are chosen both because I have easy and regular access to them, and because the per node hardware is very similar for both of them. So they both have 36 core, 2.1 gigahertz Broadwell processors with 128 gigabytes of RAM. And so what that means is that, really the difference between these systems is the network, both the underlying hardware and the software stack on top of them. So we can do pretty apples to apples comparisons. And those are the two main systems we're going to look at. We're also at the end going to show results for other networks to look more at performance portability. And that's going to be on Cray CSs with modern InfiniBand, 100 and 200 gigabit per second. And then since not everyone has access to these high-end HPC systems, we're also going to take a look at what does it look like if you run in the public cloud, running on Amazon's AWS clusters with 25 and 100 gigabit per second Ethernet. So for this talk, we're going to start by looking at NumPy versus Arkouda performance. We're again then go into some background and context for sorting, which used to use small messages, and we're going to see why they did not perform well and what we've done with message aggregation to improve that. And then we're going to look at the performance of that aggregated work, and then finally go on to some future work. So this talk does assume that you just watched Bill Roos's keynote on Arkouda. If you're watching this outside of the context of CHIUW 2020, I highly recommend watching that first. But at a high level, Arkouda provides NumPy-like arrays at HPC scale. And so what that means is that you have a Python front end that provides NumPy and Pandas-like interfaces, and it's backed by Chapel. And it's backed by Chapel in order to take advantage of Chapel's performance and scalability. And so taking a look at that, we're going to first look at performance of Arkouda compared to NumPy. So this table here is going to summarize that performance, and it's going to be performance normalized to NumPy. And so what that means is that a value of 1 is on par with NumPy, and for instance, a value of 2 is 2 times as fast as NumPy. And this is going to be for 8 key benchmarks. And so what we see here, first looking at Arkouda serial, or single-threaded performance compared to NumPy, is that by and large, performance is kind of on par. We can see that we're 2 times ahead for sorting, 2 times behind for gather, and other operations like reduction, scan, scatters, and stream triad are about on par. And this is actually a really good spot to be in. You know, NumPy has been pretty optimized over the years, and under the covers, NumPy is implemented with C and Fortran. So being able to be competitive with that relatively tuned NumPy implementation is a really good place to be. Especially because, you know, as Bill had mentioned, Arkouda was really developed by 2 initially part-time people over a couple of months. So it had to be written in high-level maintainable Chapel. So it's great that this high-level maintainable code can compete with this, you know, pretty hand-optimized code. And while we care about serial performance, ultimately what we care about is going parallel. So throwing in some parallel but still single core numbers here. We start to see that at 36 core, we see some significant speedups. So we see, you know, 16, 17x speedups for sorting, 10x speedups for gathers and reductions, and non-trivial improvements for these other operations. And then ultimately, where we want to go is distributed performance. So looking at our 512 node XC, that's 18,000 cores. We start to see, you know, just some truly massive speedups, almost a 2000x speed up over NumPy for sorting, and orders of magnitude improvements for these other operations. So as I mentioned before, this talk is going to focus on sorting since that's a critical operation. So we're going to take this row of this table and turn that into a graph. And so what we see here again is still, you know, we have our performance scalability up to 512 nodes, and we're really seeing, you know, really good performance and scalability on this XC. At the high end here, we have 110 gigabytes per second at 512 nodes. And what that translates into is being able to sort 8 terabytes of data in just over a minute. So we're able to operate on, you know, some pretty massive data sets within reasonable amounts of time. And today, this performance is portable to InfiniBand systems. We see similar performance on a 32-node Cray XC with Aries and a Cray CS with InfiniBand. And our green line here is our Aries, and the blue line is our InfiniBand. And so this is the performance we have today. But if we look back 6 months ago, the performance was very different. So we see this dashed green line is our Aries 6 months ago. Performance was still respectable, but it's 2 times slower than it is today. And then, you know, again, our dashed blue line here hugging the x-axis was our InfiniBand performance. And the performance itself was bad, but we also had no scalability, which means that adding nodes did not improve performance, which is a real problem. And so we're going to delve into, you know, why was performance so bad before? And to do that, we need some context for sorting. So the sort implementation in Arkouda is a pretty simple 100-line least significant digit radix sort. And least significant digit radix sort is great because it's easy to parallelize, but it has a ton of communication. So we have, you know, big O WN, where W is the number of digits, where Arkouda uses 16-bit digits, and N is the number of elements. So for example, if you're sorting a 50 billion element array of 32-bit values, say you're sorting IPv4 addresses, that's going to require 100 billion 8-byte messages. And that's just not something that most networks are designed for. Most networks want to take large chunks of data and take advantage of bandwidth over the network instead of doing these very small messages that require good latency and good injection rates. So that's just not something most networks are optimized for. We've already seen that, you know, Aries is pretty capable for that, but most networks are not. So what we want to do is we want to improve our performance of sorting on multitude of networks without really sacrificing that maintainability and the simplicity of this sort. And so for these 8-byte messages, previously Arkouda was using this unordered copy for them. And unordered copy is just a copy that's optimized for when you know that no overlap is going to occur. So to take a look at the performance of this, we're going to look at a simplified example. So instead of looking at sort, we're going to look at the performance of just transferring a 32 megabyte local array to a remote array. And we're going to look at 2 mechanisms for doing that. So here we have our bulk communication, where we're doing remote array equals local array, where you want this to turn into a single network put. And we have our unordered operations like Arkouda uses. So here we have our for all RL in zip remote array local array. do your unordered copy, RL. And so starting to look at the performance of this, what we see is that for bulk performance, both systems get excellent performance. On our XC, we get 8,000 megabytes per second, and on our CS, we get 6,000. So both of these networks are capable of multi-gigabyte bulk transfers, which is great. But if we throw unordered into the mix, what we see is that the XC achieves around 500 megabytes per second, which is still decent, but it is a 16th of what you can get with the bulk transfer rates. And the real problem here is the unordered performance on the CS. So here we see we're around 2 megabytes per second. So significantly less than the bulk transfer rate, and is 250 times slower than the XC unordered rate. And this was really the core of why sorting performance was bad when we started 6 months ago. And so what we see here is that we can't get away with doing these small 8-byte messages. We need to send larger messages, but we don't want to significantly change our implementation. So what we settled on was doing small message aggregation. And so we're going to take a look at what that looks like for the user code. So same as before, we have our bulk transfer and we have our unordered transfer. And this one at the bottom is now what our aggregation or small message aggregation looks like. So we have the same for all loop that we had before. And now we're using a with clause to create an aggregator for each task. So because our destination is the remote array, we're going to create a destination aggregator, and we're aggregating integers. So we create an aggregator, and then within the body of the loop, instead of doing unordered copy, we're doing this ag.copy. And so here you can see, it's a pretty modest change to the source code here. And if we look at the performance for this, we can see that the aggregated performance is around 2,000 megabytes per second, which is about 4 times faster on the XC than unordered, and almost 1,000 times faster on the CS. And so significant performance improvements compared to unordered, and we're within a factor of 4 of the bulk communication rates for both of these networks. So we kind of achieved what we were looking to do. We want to have significantly better small message performance through this aggregation, but we don't want to make huge dramatic changes to the source code, and this allows us to do that. And so I wanted to take a brief look at how this is implemented under the covers to give you a sense of what this actually looks like. So delving into the implementation a little, we have this buffer size that's a config const. So by default, we're going to buffer 4096 or 4K elements, and we'll see why that was chosen in a second. And then, so we're aggregating calls to this copy routine, which takes our destination by reference and a source value. And this is optimized for when the source is local and the destination is remote. And this is not parallel safe. It's expected to be created on a per task basis, and that's why you were seeing the with clause in the previous slides. And then there's pretty high memory usage because there's per destination buffers. And what that means is down here, if you take a look at this buffer declaration, we're creating a remote buffer for each locale. And then each locale has this 4096 buffer, and we're buffering the address of the destination on its locale and the value that we want to store there. And so here, if you're buffering integers, this is 16 bytes for the address and the value times our 4096 element size times the number of locales. And then each task has one of these. So if you're looking at 512 nodes with 36 cores per locale, that's a gigabyte of memory used just for the aggregators. And so that's why this 4096 value is chosen. It's actually pretty low in terms of the amount you're aggregating, but it allows for 1 gigabyte out of 120 gigabytes to only be used. So we were pretty happy using 1% of system memory for aggregators, but this is definitely something that we want to look at tuning going forward. So these are kind of the data structures you have, your buffers, and then you have indexes into them. And then looking at the copy implementation. So what we have again is we're taking our destination by reference, and then we have the value that we want to store that destination. And then in order to buffer this, what we do is we find our locale of the destination, and we compute the local address of that destination on the locale that it lives on. We find our index into the buffer for that locale. And then here we're taking our address and our value, and we're putting that into our buffer for that locale, and then just incrementing our index into it. So that's it. At this point, we have buffered the value successfully. And then if the buffer is full, we're going to flush it. And the flushing code is also pretty simple. We're just going to migrate our execution to the remote node using an on statement in Chapel. And then here, we're going to get the buffered data. So here, we're getting our addresses and our values. And this is the bulk communication right here. So we're now doing bulk communication of that buffer that was previously aggregated instead of individual messages. And then we just do our original assignments. And so, that's it. We have now flushed our buffer, and the values that we'd previously buffered have been written to memory. And if you look at the actual implementation in Arkouda, there's really not much more to it. We do things like we flush when you go out of scope, and we occasionally yield to improve performance. Well, that's really it. This is 100 lines of chapel code to implement this aggregation as a library. And as we've already seen, this significantly improved performance. We saw that, more than a 2x performance improvement on the XC, and that 1000x performance improvement on the CS. And with such a relatively simple implementation, that does raise questions about its scalability. But happily, we've seen good scalability despite its simple design. So this is looking at 512 node performance on an XC, and we see that we have about a 1.8x improvement, switching from not aggregating to aggregating. So good scalability despite its simple design. And so that's kind of the performance that we see on our CS and XC. And then we also wanted to take a look at, what's the performance like on other networks? And so this next section is going to be a little bit about the performance portability. So previously you saw InfiniBand Performance for a 56 gigabit per second network. 56 gig is actually a little old. That's 3 generations ago, but it's what we had easy access to. So we wanted to take a look at 100 and 200 gigabit systems as well, since that's more modern. These were all collected using 36 cores as well. Technically, the 200 gigabit system has 48 cores, but we only used 36 to try and have a fair comparison. And so what we see here is the solid blue line is the line that we have been seeing. That's the 56 gigabit per second. And then the dash blue gets to 100, and then dotted one gets up to 200. And it is worth noting here that I did have to increase the buffer size from 4K to 8K to see these performance improvements. And you do see modest improvements going to these newer generations of hardware. Given the significant increases in bandwidth available to the system, you would have expected these to be higher probably. And so what we think is that we're probably not bandwidth bound anymore. There's probably something else in the aggregation implementation that's limiting us. Probably that we're doing synchronous aggregation instead of something asynchronous or something along that lines. So that's definitely something we want to look at going forward in the future. But still today, happily, with these newer generations of hardware, you do get a slight performance boost. And then as I had mentioned before, not everyone has access to these high-end, high-performance computing interconnects. So we also wanted to take a look at what's performance like on a publicly available system. And so these results are going to be collected on AWS, Amazon's web service. And this is going to be with 25 and 100 gigabit per second Ethernet. And I do want to know, this is really the first time that we've run seriously on AWS. So these numbers are kind of fresh. So these were collected on a 36-core C5 18x large instance. The names are kind of meaningless, but it's basically compute optimized 5th generation, and 18x large just tells us it's going to be 36-core. And that's the 25 gigabit per second Ethernet. And then we also ran on a C5N, where N is networking optimized. And this has Amazon's Elastic Fabric Adapter, or EFA. And EFA is Amazon's take on an HPC NIC. So here we're going to be comparing, kind of very commodity 25 gigabit Ethernet and this 100 gigabit with their take on an HPC NIC. And so looking at the graph here, we see in green here is our XC line just thrown in for a point of reference. And then we did have to increase the buffer sizes pretty significantly for these other ones. But then looking at the networking optimized one with EFA, we see, decent performance and still good scalability here. So we are around, 4 times off from the XC, but that's actually pretty good performance considering that we've done no tuning here. And then looking at the truly commodity 25 gigabit Ethernet, it's around 10x off from the XC numbers, but still, considering we've done no tuning here, this is, good, decent performance, and kind of more importantly that, we're still seeing scalability. So if you continue to add nodes, you would expect continued performance. And so, this is what we've done to optimize ArcSort. Beyond ArcSort, we've also done some other optimizations to Arkouda. If you want to learn some more information about that or just some other performance results, you can take a look at the user optimization deck from our recent release notes. If you want some information just about general performance optimizations that have been done to Chapel, many of which have benefited Arkouda, but also benefit all Chapel programs, you can take a look at the performance optimization deck. And if you just want some general performance and tuning tips, you can take a look at the main performance landing page. So going forward with going forward with this work, what we really like to do is collect Dask performance numbers. If you're actually running Python at the scale, you're not just running NumPy. What you're doing is running Dask or something like it in order to get you that distributed and parallel performance. We believe that Arkouda is significantly faster than Dask, but we really only have anecdotal evidence for that. Operations that would take a few seconds in Arkouda were timing out for us after a couple of hours in Dask, but we're not Dask experts, so we'd really like to collaborate with somebody who is in order to get some earnest benchmark results and see how we stack up. For our own work, we'd also like to take a look at optimizing the aggregation performance and reducing the memory footprint. As you saw in some of those performance portability graphs, we had to manually increase the buffer size, but we'd really like that to be automatic. So do some sort of auto tuning for that buffer size on startup. And then we can do other things to improve the performance. We could aggregate within a node before sending it over the network. We could do asynchronous aggregation and other things like that. We'd also like to take a closer look at tuning performance for some of the commodity Ethernet networks and some of the newer InfiniBand networks, because we believe the performance can be much higher there. And lastly, aggregation isn't just something that's useful to Arkouda. It's generally useful to, Chapel users. So we'd really like to add aggregation to Chapel standard library. And then as part of that, don't just have copy aggregation, enable arbitrary message aggregation as part of that. So that's what I have for you today. We've seen that message aggregation can enable a high performance sort in Arkouda that's portable to a wide variety of networks. And we believe that there's significant performance optimization opportunities that remain. And this final graph just kind of shows you the InfiniBand numbers, the Aries numbers, the EFA numbers, and the Ethernet numbers all in one. And that's what I have for you.
Cool. Thanks very much, Elliot. If you've got any questions for Elliot, either about this talk specifically or about performance more generally in Chapel, please type those into the Q&A tool. Elliot, if you're not seeing them, there's some very cools and nices being posted in the chat. I'll start out the questioning. You kicked off the talk talking about how you're both the pit bull in the good way and the bad way. The bad way being sometimes not letting go of something. So my loaded question to you, given that I work with you, is what is something currently that you're locked onto that you should really be letting go of and moving on to? And what's something that deserves some attention in the next 6 months, say, performance-wise from you, that you're hoping to turn your attention to?
Why do I feel like that's a trap of a question? So the types of things that I can get a little bit obsessed with is, we saw on some of the early slides where serial performance wasn't quite on par with NumPy. And so I've been kind of obsessed, okay, so like looking at the scan number, why are we off? And delving into the implementation to figure out where we're losing that. And it turns out it's because we're doing some default array initialization. And so I get kind of fixated on those sorts of things where it's like, yeah, we're 20% off here, but does that really matter when what we ultimately care about is, performance at scale? So those are the types of things, but it's kind of good and bad, right? You need that sort of ability to continue to dive until you hit bottom for some cases, but then it hurts you in others. Something that I think we need to look at, we have a kind of a long-standing issue where if you're using distributed classes, or if you're using distributed arrays in a field, that can add a lot of unnecessary communication. And I think that's a case that could really benefit from some attention. But kind of higher level than that, I think what we really need to focus on is user tools so that they can do their own performance optimization and analysis. I think one of the hardest things today is just figuring out why is your program slow, and we really benefit from tools that can show you, here's where your communication is, it's coming from these lines, and maybe you have too much allocation here or something along that lines.
Okay, great. Along those lines, I know that at least some of the applications talks we'll hear later on today, I think are running into performance issues and they're not fully diagnosed. I wanted to encourage anyone on this call who is using Chapel or interested in using Chapel to definitely feel free to call on our team to help out with any performance mysteries you're wrestling with. We recognize, as Elliot said, that sometimes you don't have the tools to do it all yourself, and we're happy to help fill in those gaps. Elliot, there's a question that came in on chat about, are there any is there any fundamental optimization being done in the language level or the compiler or in current work that relates to the previous work you might remember from Lewis and company on the Chapel aggregation library?
So I'm not sure I totally understand the question, but let me take on that. Um, so in comparison to the Chapel aggregation library, and the reason that we didn't use cal to start was because we were mostly looking for something that was just for copy aggregators. So we had a much narrower view of what we needed to do. And we needed really fixed performance and memory usage guidelines. So for instance, I think cal was focused on being able to do more arbitrary aggregation. And I think that's work that we're going to lean on as we look to bring this aggregation back into Chapel proper. But for now, we needed something that was kind of very fixed and had easy to reason about scalability limitations. In terms of work being done in the compiler, so we've done some previous work to enable automatic unordered operations. And I think what we want to look at is, and I think Brad showed a slide at the very beginning that was RA atomics with unordered operations, and that had some nice performance benefits. But that's also something that really benefits Cray Aries networks, but might not do so well on other networks. So we want to look at, can we enable this aggregation automatically instead of just using the unordered operations?
Okay, great. And then a question that came in from Tyler on chat with respect to our discussion about the difficulty of determining where your performance is going. He asked about Chapel Viz for profiling. Is that still being developed? Maybe you could comment on ways in which that does or does not help you in your work, for example, Elliot.
Yeah, so Chapel Viz was an external contribution, and I think that laid a lot of really good groundwork for collecting the sorts of profiling information that you want. I think you still want the ability to kind of profile your entire program. For Chapel Viz, you kind of have to specify which regions do you want to profile, and it can show you information about that. But what comes to mind for me is you kind of profile your entire application, and then you can start peeling through, see which functions have communication, and kind of get this line has X number of COM events or this number of memory allocations. And I think Chapel Viz provides some of that. I don't think it's being actively developed, but I think that sort of tool and probably a command line version of that would be really valuable.
Yeah, so specifically for those who haven't used Chapel Viz, as Elliot said, you kind of put these calipers into your program to measure things, but you find yourself doing recompilations all the time as you're squeezing those calipers down. And a lot of good profiling tools, you just sort of profile the whole thing and then sort of surf the results. And I think that's something that we'd really like to see more of in Chapel tooling. Okay, cool. Elliot, thanks again for giving the talk and for all the hard work on performance, obviously. And that wraps up our Arkouda session.